Great. So today we're very lucky to have Sebastian Mizera from the IIS for today's particle theory seminar, and he's going to tell us about unitarity cuts of the worldsheet.
All right. Well, thank you so much for this introduction. It's a real pleasure to be here, and thank you for the invitation to give this seminar. Today, I will be talking about work together with my fantastic collaborator, Lawrence Eberhard, who's also at the IIS. And some of the parts some of the results that I will present today are very much work in progress, but many of them already appeared in this paper from around 2 months ago under the same title as the title of this talk. So let me preface the first part of this talk by saying that actually surprisingly little is now about scattering of strings beyond the low energy limit. And this is something that we wanted to improve, take steps into improving in this talk. So to emphasize this point, let me flash you the simplest scattering amplitude in string theory that we know about, which is the famous Veneziano amplitude. Veneziano amplitude computes the contribution to the planar scattering at tree level, and itself is a function of two Mandelstam invariants, S and T, where S is the center of mass energy squared, and T is the momentum transfer squared. Okay, here's how it looks like. It's a collection, or it's a ratio of gamma functions. The gamma functions in here depend on the alpha prime, which is the inverse string tension, as well as the S and T. Okay, everything is multiplied by this prefactor that historically is known as the T8 tensor, and it encodes all the polarization dependence of this amplitude. So it involves contractions of the external momenta P, as well as the polarization vectors epsilon, instead of combinations like this. Okay, but this is the most interesting part of this amplitude, the gamma functions. In fact, from the Veneziano amplitude, you can read off a lot of physics. So, for example, it would tell you about the spectrum of string theory, the fact that there's poles at every integer in S and T. Also, you can read off from it, for example, the low energy limit. So as alpha prime goes to 0, you recovered the classic Yang-Mills amplitude. When you take the Regge limits, so T goes to 0 at finite S, it tells you about the spin dependence of the spin content of the theory. Similarly, you can go to high energy limit. It tells you about the exponential softness. You can also study unitarity, which would tell you about the critical dimension. Anyway, it's an amazing formula, but the sort of sad state of affairs is that we actually have no counterpart of this beautiful formula currently at the loop level. And this is something that we wanted to take steps in improving in this talk. But before going to loop level, let me just answer a simple question that's kind of very natural when you see the Veneziano amplitude.
Question about what did you mean about no counterpart is known at loop level? Can't we do string one loop scattering?
I will come back to the answering this question. In fact, most of this talk will be answering this question. Okay, so for now, let's ask the very simple question at the level of the Veneziano amplitude. Why is it so much better than its worldsheet formulation? So if you're familiar with the superstring theory, then this integral here represents the integration of the moduli space of punctured disks, and Z is the cross ratios between positions of vertex operators on the worldsheet. Okay, if you've never seen this, then don't worry. It's just some specific integral that you can do. It's integrated between 0 and 1, and it gives you the gamma functions that we've seen on the previous slides. Okay, so let's say you wanted to actually compute this amplitude, meaning that you wanted to plug in some specific numbers for S and T, and then just numerically compute what that amplitude is. Well, recall that in the physical kinematics, the one that corresponds to the real scattering with the real energies and angles, S is the center of mass energy squared, so it has to be positive. And likewise, T and U, the other Mandelstam invariants, have to be negative because they represent the transfer momenta, which are space-like. Okay, what this means in particular is that Z here is raised to a negative power. So, and it's integrated all the way to 0. And that, of course, raises an immediate concern that integral doesn't converge whenever S is positive. What this forces you to do is go to a different kinematic region, for example, when S is negative and T is negative and other things like that, evaluated the amplitude there, perhaps analytically in terms of the gamma functions that we've seen before, and then take this result and analytically continue it back to the physical kinematics. So you're forced to think about analytic continuation in external parameters to begin with. Let me perhaps mention that this is a sign of a much more general problem. It's not limited to 4-point, it's not limited to tree level. And it's related to the fact that usually the definition of string amplitudes that you would see in textbooks are as follows. So let's say we wanted to compute an amplitude for a genus G contribution with n external points. So it's something that depends on n external momenta. The prescription that you would find in any book on string theory is that you first compute the correlation function of vertex operators, do all the spin sums and so on. And then what you need to do is integrate that answer over either the moduli space of genus G Riemann surfaces with n punctures, or perhaps some middle dimensional cycle in this moduli space. And unfortunately, this tentative prescription isn't actually entirely correct. One quick reason to see that it's not correct is that, at least for example, genus 0 or 1, you would end up with functions here, these correlation functions, which are entirely real, and the integration cycle would be real as well. In fact, sometimes it happens that they're even positive, so even worse. This is, of course, not consistent with unitarity, because we know that any scattering amplitude it has to have an imaginary part to be consistent with the optical theorem, for example. And the place where this trouble comes in is at the definition of the integration contour. So this integration of the moduli space or these middle dimensional cycles is only supposed to be treated as a kind of a formal definition, and it cannot be usually used in practice. Okay, and what we wanted to do in this talk is that, at least at genus 1, so G equals 1, to be able to prescribe what the actual contour is supposed to be for various string theories.
I seem to remember some unitarity checks even in Polchinski between genus 1 and genus 0. Can you elaborate on, can you state a little more precisely what was known before?
Yes, I'm going to come back to this in a second. The basic checks that have been made are in the low energy limit, so as alpha prime goes to 0, in which these problems with not knowing the precise definition of the integration contour can be sort of circumvented in various ways. I will come back to this in a second. Perhaps before that, let me mention that physically the underlying problem can be traced back to the fact that we formulate the string amplitudes on a Euclidean worldsheet, while the target space is Lorentzian. For the purposes of this talk, we'll take the target space to just be in space. Of course, the reason why we use the prescription with the Euclidean worldsheets is that we want to be able to use the CFT technology to manifest the fact that there's no UV divergences and similar topics. But that has a disadvantage of obscuring things like unitarity, which are important when you work with Lorentzian target space. And here to answer the previous question, or this hint at the answer of the previous question, why hasn't this been a problem before? After all, people have computed a lot of explicit results in string perturbation theory. So let me perhaps mention two corners that have been explored before. The first one is the tree level. So at tree level, these scattering amplitudes are simply meromorphic functions, so they have only isolated poles. It's very easy to analytically continue a meromorphic function. So in a sense, the troubles with the integration contour are not necessarily as severe, or they can be easily dealt with. Another corner that has been explored by many people in the past 40 years is the alpha prime goes to 0 expansion. In the alpha prime goes to 0, even if you're not careful about the integration contour with the correct I epsilons, you can match them simply by the sort of treating string theory as an effective field theory, just adding higher derivative operators to your supergravity or superannulus action, and then match the positions of the branch cuts that way. Okay, so in both of those situations, you can actually get away without knowing the exact form of the integration contour. But what we wanted to do today is evaluate the string amplitude at some finite point, be able to basically numerically compute it at some finite alpha prime. Okay, so what does it mean to compute the amplitude? For the purposes of this talk, I will just give you a very pragmatic answer. As I mentioned before, what we want to do is be able to efficiently evaluate it numerically. And this can be realized in many, many different ways. For example, you can realize that some of the string amplitudes are some known hypergeometric functions. In this sense, the Veneziano amplitude answer is of this type because we have the gamma functions, and we know that gamma functions can be fast evaluated in a fast way. Perhaps you want to map the string amplitude into some fast convergent integrals or infinite sums, anything that gives you numbers out of the amplitude. Okay, so in most of this talk, we'll focus on the imaginary part of genus-one amplitudes. And let me flash you what the final result will be. Final result would be that for any value, physical value of S and T, we'll be able to plot the amplitude and read off some physical properties out of these explicit computation. So I believe that this would be the first result of this kind. And let me stress that the previous computations have been mostly contained in this corner here. When we expand in the low energy, meaning that both S and T being very small, instead of expanding around this tip. Okay, so here's the outline of this talk. So the talk will be divided into 4 parts. In the first part, I will come back to this question of analytic continuation from Euclidean to Lorentzian signature. And the result of this part would be our new proposal for the correct integration contour for genus-one amplitudes. Then once we have that, we'll move to the unitarity cuts of the worldsheet, something that is needed to compute the imaginary part, where we will use this prescription for the integration contour from the first part to actually explain how to do the computations. So this will be a more technical part of this talk. And then we'll move to a more physical part, number 3 here, which will be, once we can actually evaluate it numerically, what kind of physical properties can we read off from the imaginary parts. And there will be some surprises in this part, and we lead to some notion of something called the low spin dominance that I think it's a very interesting feature that we observed for the first time.
Sorry,
okay, there's a question, yes.
Yeah, so is this also, these issues arise at genus 0 as well, or this is only at higher genus? Or?
Yeah, the issues arise at any genus, including genus 0. But as I said, sometimes you can get away without dealing with them properly. Basically, because you can evaluate the amplitude sometimes in an unphysical region without being careful about the integration contour, and then analytically continue back that answer. Okay, and then if there is time, depending on the number of questions, we'll have a glimpse at the real part, so not computing just the imaginary, but also completing it with the real part. And the computation of the real part will involve the most complicated contour deformation I've ever seen in my life. So hopefully we'll get there on time. And I should probably mention that all the questions are very much welcome, so feel free to interrupt me with questions. Okay, so since there were a few questions about this, let me come back to the question at tree level. So from now on, I will be setting alpha prime equal to 1 for convenience. So as we've seen before, the amplitude in type 1 string theory is computed using this integral. And we've also seen that the problem arises when z goes to 0. This is the region in the moduli space where the puncture 1 and 2 collide, or in other words, it corresponds to the S-channel exchanges. Okay, since we're interested in the neighborhood of z goes to 0, let me change the variables to this, e to the minus tau. And in the tau variables, we're interested in the tau going to infinity limit. Let me mention that tau roughly measures the proper time of the probe that developed in the Riemann surface. Anyway, after you do the change of coordinates into tau, this integral here becomes this integral, and then we can expand it in these parameters into the minus tau. Okay, then you might recognize this hash. These are some numbers here, and you might recognize that the the first integral here, e to the tau s integrated over d tau is giving you 1 over s explicitly. So this is the masses, where the masses exchange comes from. Then the next term in the expansion is the same integral, but s is shifted to s minus 1. Okay, so that after integration gives you the level 1 poles and so on, you get level 2 and all the power of exchanges. Okay, at this level, we have to make an important distinction between, very subtle but important distinction between Schwinger parameterizing a propagator. As we know from field theory, we can do it in 2 different ways. The first one is using the Euclidean proper time, this tau sub e, in which case the Schwinger parameterization of the propagator would look like this. And in the second option, we can also integrate over the Lorentzian proper time, which just amounts to adding an I in this integral and being more careful about the I epsilon. So this, of course, inspires what the correct prescription for the integration contour should be. We naively integrate over the Euclidean proper time, but whenever a problem arises, you're supposed to continue back to the Lorentzian signature. And this is, in fact, what tells us about what is the correct integration contour in our variables for the Venetiana amplitude. Let me pick some large cutoff, tau star, which is some large number, and I'm going to claim that I have to integrate all over to this tau star and then turn into the upper half plane, and this will correspond to the locally Lorentzian worldsheets. Okay, back in the z variables, which remember they were related to the tau by the exponential map. What we have to do is integrate all the way up to some small number, this number here, and then mapping this contour in the upper half plane by the exponential map leads to this infinite spiral. In fact, you can be even more clever about this. What happens here is that we have the first spiral. So let me represent it by this integration contour. And then we know that there's a branch cut starting at z equals 0. So as you go around this branch cut, you just pick up a phase which is related to the Mandelstam invariant S, and then that phase is multiplying the same contour. Then as you do the second loop, you pick up the phase twice, so you end up with this factor, and so on and so on. Now the series you can simply resum. This is just a geometric series, and the correct integration contour will involve this residue times this factor. Of course, from this factor, we see that whenever S is an integer, you have a pole. And this, in fact, is what tells you about the infinite number of string resonances from this contour perspective. Okay, so this inspires a strategy for finding the correct contour of integration at higher genus. So that strategy was proposed by Edward Witten around 9 years ago. It consists of 3 parts. First of all, you're supposed to identify local variables, let me call them Q, that look like the exponential of minus the Schwinger parameter. So basically matching how your worldsheet looks like in terms of the would-be Feynman diagram. And then once we've identified that local variable that is supposed to be the Schwinger parameter, we continue to Lorentzian signature locally in the moduli space in exactly the same way that we've already encountered at genus 0. And then the final step is to glue everything together. And perhaps let me emphasize that here, actually, the final step is the one that is the most difficult one to pull off in practice. And the reason why that procedure has never been implemented since this proposal. Okay, so if there's no further questions, let me move on to the explicit formula for the genus-one superstring amplitude. So in this talk, we'll focus on the planar annulus contribution. So you can find the details of the other contributions, including the Möbius strip and the torus and the non-planar contributions in the paper. So let me remind you that the planar annulus contribution is the one in which we have the annulus, and we insert 4 punctures on the outer boundary of this annulus. You can, of course, map it to this rectangle that depends on the modular parameter tau. So tau being very small corresponds to this annulus being very thin, and the tau being very large imaginary corresponds to the annulus being very thick. And the other moduli that you have in the game is Z1, Z2, Z3, and Z4, which are the positions of the vertex operators. And using translation invariance, you can fix one of those. For example, Z4 is equal to 1. Okay. So then the leftover integral that you need to compute for the planar annulus contribution looks something like this. So we integrate over the modular parameter all the way from 0 to I infinity. And then we integrate over the positions of the vertex operators in this specific order. So this specific order selects the planar ordering of my scattering amplitude. There's the prefactor, the T8 tensor that we've already seen at the genus-0. And then all the interesting stuff happens in the integrand. So this is the integrand after doing all the OPEs and doing all the spin sums. I've already done that for you, and this is the result. The result can be expressed in terms of the Jacobi theta functions that depend on z and tau. Okay, so Jacobi theta functions are some elliptic functions. If you've never seen them before, then the exact definition is actually not going to matter that much in this talk. But they have some infinite sum representations. Okay. In the integrand here, we have two factors. The first one raised to the power of minus s, and the other one to the minus t. And each of these factors is some cross ratio of the coordinates of the vertex operators. Okay, this one and this one. Okay, so this is a tentative, so this sort of very formal definition of the string amplitude. It's something that you cannot put on a computer. This integral actually doesn't converge. So what we wanted to do is learn how to perform this Witten procedure of analytically continuing locally in the moduli space. So the first step in that is identifying various degenerations in which you need the I epsilon. Okay, so there are these first three degenerations are the ones that are kind of very easy because they locally look like the same as what happens at the genus-0. So let me go quickly through them. First of all, if Q, this small parameter, is the difference between positions of the punctures in 4 and 3, then this place in the moduli space, it looks like developing a small throat, so like exchanging a massive particle in this channel here. All right. Then you also have this contribution from the wave function renormalization, in which case the 3 points here are squashed to be the same. And this diagram looks like a bubble contribution to a Feynman diagram, and it computes the wave function renormalization contributions. Similarly, you also have the tadpole contributions in which 4 punctures go on top of each other. Okay, so these 3 are sort of morally speaking the same as genus-0, and in that sense, we already know how to deal with them. What we're looking for are the new features that appear first time at the genus-1. And the first feature that appears here is the so-called non-separating degeneration, which corresponds to pinching one of the cycles of the torus, of the annulus in this case. Okay, so as is well known, you can identify the places in the moduli space where this degeneration happens. And the small parameter, it turns out that you have to take is this exponential of minus 2 pi I over tau, where tau is the modular parameter. We'll see that this degeneration and correspondingly implementing the correct I epsilon prescription for this is going to compute as the unitarity cuts of the worldsheet. Okay, so for the purposes of this talk, what I wanted to do is focus on the part of the contour that lies in the fundamental domain, tau. So as we've seen before, tau is taking this variable where star is some large cutoff that you integrate to. And then after you reach this large cutoff, you switch on the imaginary part and you add it here. Okay, so our original contour that used to run from 0 all the way to I infinity, now with this deformation from the Euclidean to Lorentzian is going to look like this. You still integrate all the way here to 0, except you stop at some small value, small imaginary value. And then after mapping what this integration contour looks like, you find that this imaginary part adds this hook to the endpoint of your integration. Okay, the reason why the shape of this contour matters a lot close to the 0 is that the elliptic functions that are featured in the integral have the essential singularity at zero, in fact, at every rational point. So this is the reason why it actually matters how you approach this point. And what the I epsilon prescription tells you is that you're supposed to approach it from the right. Okay, then as we know, the string theory would not be self-consistent unless you add the Möbius strip contribution. After you add the Möbius strip contribution, it turns out that the integrand that you need to integrate looks exactly the same. The only change that happens essentially is that you need to shift the tau by 1/2. So you basically take tau and they shift it to tau plus 1/2 and reverse a sign. So the corresponding integration contour is going to be this one. So the first one was responsible for the planar annulus contribution. The second one is responsible for the Möbius strip. And once again, implementing the correct I epsilon, it corresponds to adding this small loop in here. Okay. As we know, these two integration contours meet at the I infinity. The place in the moduli space that corresponds to I infinity is the one that corresponds to emission of a closed string pole. And it is, of course, well known that if you sum over these contributions and the gauge group has the correct rank, so it's SO32, then these contributions cancel out at infinity. Okay, so what this means is, in fact, as you can check by direct inspection of the string integrand that we've seen before, there are actually no poles anywhere in the upper plane. So what this means is that we can close off the contour in the upper plane, and we can actually keep deforming it down. In fact, you can deform it all the way to this contour that is presented here, and that contour, in fact, constitutes our proposal for the correct integration contour in string theory. And this is the one that I'm presenting here is for the planar contribution, but we also know how it looks like for the non-planar or for the torus contributions. So once again, the precise shape of this contour doesn't matter. The only thing that matters is that it starts at 0, ends at 1/2, and the endpoints are approached from the right, from the correct direction. In fact, we'll come back, if there's time, I will come back to this integration contour at the end of the talk, and we'll learn how to deform it into this fractal pattern that we've seen.
Can we say a little more globally what we're doing in the moduli space of punctured surfaces? Like, are you just presenting a particular compactification that is not the standard Deligne-Mumford compactification? No, not really. We're just choosing a particular contour, particular middle dimensional cycle in the moduli space. And that middle dimensional cycle. I thought we often integrate over the entire moduli space.
Yeah, this is so for the open strings, you need to select the middle dimensional cycle. In the case of the closed string, would integrate over the entire moduli space. There's a different prescription, something that is more complicated, so I didn't want to describe here, in which we first need to complexify the moduli space. So take the two copies, the holomorphic and anti-holomorphic copy. Then the original integration cycle would be the one that is on the diagonal of this complexification. And there we can deform the contour separately in the real and imaginary part in a very similar way to what we're doing here. So in that case, we would have a middle dimensional cycle in the complexification of the moduli space.
But isn't it just I'm confused why it's not just a compactification of that moduli space, because aren't the only singularities sort of at degenerations of the Riemann surface? The integral converges away from those. So if you were to just hard cut off away from those degenerations, you would have a finite answer.
That's correct, but that answer would be also meaningless because it would depend on the cutoff. So,
well, my point is that it seems like all the information is contained near the degenerations, so therefore it could be just interpreted as specifying a particular compactification.
Well, technically speaking, what we're doing here is we're specifying a particular integration contour, and the compactification wouldn't know about. Compactification only knows about the topology of the moduli space. It does not know about the S and T dependence, for example. And as we'll see, the integration contour has to know about the how new thresholds open up something that is an information on top of the compactification. Perhaps we can discuss this point afterwards. Okay, so this was in fact a good stopping point. Let me, as I mentioned at the beginning, in this talk we wanted to focus specifically on the imaginary part of the amplitude. So let me rewind back one slide here and ask what would happen if we didn't compute the plus I epsilon, but instead if we did the minus I epsilon, so the complex conjugate of the amplitude. Of course, what would happen is that we would have to select a similar hooks, but add them in a different direction in here. And now you see what happens when we compute the imaginary part. We take these original contours minus the ones with the reversed hooks. So we end up with the contours that look like that. So these are the contours of integration. If you just wanted to focus on the imaginary part of the amplitude. And these are circles, once again, anchored at 0 and 1/2. And once again, the size of the circle doesn't really matter. The only thing that matters is that they touch the singular points in here. In fact, we'll make heavy use of the fact that the size of the circle doesn't matter. We can shrink it to be arbitrarily small, but not 0. And this will be very, very useful for our applications. And we'll see that these contours compute the unitarity cuts of the planar, annulus, and the Möbius strip contributions, respectively. Okay, so at this stage of the talk, we went through the sort of brief overview of the continuation, and now we'll use this information to compute the unitarity cuts. Okay, so let me remind you about the unitarity cuts. That the unitarity embodies the physical principle of probability conservation, and it's given by this equation SS dagger equals 1. Then we, as usual, we isolate the interacting part of the S matrix called the T, and then the statement of the optical theorem is this one. It actually turns out that for the purposes of doing analytic continuation, it's much easier to work with this holomorphic version of unitarity cuts, but I will not, I will refer you for details to this paper, and I will not skip over this detail in this talk. Okay, so we can illustrate everything at this level of this cartoon. So if we want to compute the imaginary part of the genus-one contribution, then it can be obtained by gluing 2 genus-0 contributions by 2 lines. Okay, these 2 lines are the on-shell particles that go between left and right. As we know in string theory, the masses squared are quantized as integers. So what you have to do is sum over all these integers. You have to sum over the whole spectrum, the degeneracy, the polarization vectors, and so on. And we also know that the new threshold, we expect that the new threshold opens up whenever the masses of these particles cross, when the energy crosses this combination. Okay. So at this level, we have basically 2 options. One is we can do unitarity cuts, so to say, by hand, just as in field theory. So knowing the 2 genus-0 contributions, we can glue them together, perform all these complicated sums. We'll see that that's actually not a very sustainable algorithm, and basically it becomes impossible beyond the massless exchange. So because of that, we'll turn to the worldsheet, to these integration contours that we've seen before, and we'll let the worldsheet do all the work for us. Okay, so let me first sketch what would happen if we did this by hand. So these are the sort of known steps that I suspect many of you would have seen before. And let me emphasize that we can do this for the massless cut when the particles being exchanged are both massless, but it becomes very difficult beyond that. Okay, so the steps that you need to perform is that, first of all, you need to sum over all the colors, so basically connecting the color lines in all possible ways. Then you need to sum over polarizations of the intermediate states. In the massless level, we know that the critical dimension, we know that we have only gluons and gluinos. So after performing this polarization sum, which is quite involved, you find that the answer is actually very simple. It gives us this T8 tensor addressed with some kinematics. And then finally, you need to compute the loop integration. So the loop integration is the standard loop integration, and it puts two particles on shell with positive energy. One thing that you can do is stated in a more on-shell way, so as an integration of the intermediate Mandelstam invariants. So let me illustrate this at the level of a cartoon. So what we're computing here is the imaginary part of the amplitude here on the left that depends on S and T Mandelstam invariants. And then we wanted to relate it to these two tree-level contributions glued by the cut. So the total energy flowing through this diagram is the same. So all of these three contributions, this one, and this one, see the same energy as. However, this contribution here, it has some new momentum transfer T left. Likewise, this one has T right. So what it means to integrate over the intermediate phase space is to integrate over this T left and T right. Okay, so after the dust settles, let me just explain the same formula, just at the level of equations. We're computing the imaginary part of the planar annulus contribution below the S equals 1. So we are only looking at the massless exchanges. Okay, there are some prefactors. Here, capital N is the 32 from SO32. Then we have this, as promised, we have this integration of the T left and T right. There's some kernel that is given explicitly in here that convolves, tells us how to actually perform this integration over the phase space. And on the left and on the right here and here, we have basically Veneziano amplitudes, just evaluated with T left and T right. In fact, this general formula gives us an expectation what we might hope for to see from the massive exchanges. So if you wanted to compute the full imaginary part, what you expect to see is some prefactors in here, and then you would have a sum of the different mass levels, okay, say N1 and N2. We know that each new contribution is supposed to be opening up as S crosses this threshold. Then, as before, we have some integration of a T left and T right with some new kernel that now depends on the specific masses that are being exchanged. And that kernel is given here with some combinations of the Mandelstam invariants. Once again, we have a Veneziano-like factor in here and also some unknown function. So that unknown function is something that would come from these complicated sums or summing over all these spectra at the given mass level, all the degeneracies of the particles, the polarization vectors, and all that. So in principle, it could be very complicated. And in fact, we do not know currently how to do this computation directly by hand. Okay, so the only thing that we can compute here is the thing that we've seen on the previous slide, the Q00, which is just a polynomial equal to 1. This function here. Another thing that's sort of preparing to what we will see in the general structure, what I've done here is I stripped away two gamma functions from these two Veneziano amplitudes, which is now up front. Okay, so these two gamma functions give you double poles at every positive integer. We can, of course, identify physically where these double poles come from. They come precisely from the degenerations of the worldsheet that look like this. So in the tree level, this would be, in field theory, this would be a bubble diagram with two propagators. Okay, so at this level, we've stripped this singularity up front, and if you could actually find what those polynomials Q are, then you would be able to just use this as a computational tool. Okay, so at this level, there's no singularities. Everything is convergent. So you can evaluate this numerically if you just knew what these Q's were. Perhaps let me also explain a little better this integration over the phase space. So this was this integration over T left and T right. So recall that momenta transfer have to be negative. And this just gives you some integration region in this phase space that you need to integrate. And then as you go to the forward limit, for example, T left and T right are getting identified. So they're equal or almost equal. Similarly, in the other forward limit. And then as you go on the threshold, the size of the phase space shrinks to 0. So this is precisely what it means for the new contribution to start opening up as you go closer and closer to the threshold. Okay, so as I mentioned before, what we wanted to do is perform this computation using unitarity cuts. So let's focus on the planar annulus contribution, which was given by the correct integration contour was given by this circle. Equivalently, what you can do is you can map this by a modular transformation to a line which is far away. You can push this line arbitrarily far into the complex plane. And then in this under this map, the parameter q, which is the small parameter that we are supposed to be expanding about, is this e to the 2 pi I tau. Okay, so we want to exploit the fact that q can be arbitrarily small, but non-zero. After this modular transformation, we end up with the function that we've seen before, just after some shifting. And basically what we wanted to analyze is this integrand here, and more specifically, how this integrand behaves as q goes to 0. So let me say that the leading behavior in this small q is this q to the trop, which is some function that can depend on s, t, and the positions of the punctures. Okay, the reason why this function I call trop is that it's in fact related to a beautiful topic in mathematics called the tropical analysis. And it basically tells you how to find systematically these exponents. The reason why we care about this is that we know that if we find that the leading behavior of the function looks like q to the trop, q is arbitrarily small, it means that only the terms that have trop being negative, the exponent being negative, can possibly contribute to your asymptotics. Okay, so let me start with a toy model. If you just had a single elliptic Jacobi function here, we know that it admits this q expansion. But in fact, if we also know that the way that the positions of the vertex operators enter in this function is through the z. And the differences between two vertex operators, their positions, is always bounded between 0 and 1. Okay, and in particular, what this means is that out of this infinite sum, only 3 terms could possibly matter. So there's the first sum, there's the first term after pulling out q to the 1/8 up front. There's the first piece, which is q to the minus z over 2. This is the piece that always dominates. Okay, so we can see that it's parametrically larger than these ones. You can actually check that it's parametrically larger than any other contribution. However, when you go close to the boundary, so when z goes to 0, we also need to include this factor, which is now of the same order as we would have z to the 0 and z to the 0 here and here. And likewise, close to the other boundary, you need to include the other contribution. Okay, so this was a toy model. After sort of grinding through the math or going through this tropical analysis, you find that for the actual integrand that we are interested in, which looks like this, you find that the tropical approximation looks precisely like that. So it's q raised to some power. And there are these two factors in here that matter only if z to 1, meaning the difference between the positions of the first and second and first vertex operators, becoming small. And likewise, 4 and 3. Okay, so far all the computations are exact, and you can show that in fact they're supported only in some region in the moduli space, but I didn't want to get into details. Okay, so at this level you can actually identify some of the interesting variables. So for example, the position, the z to 1, I'm going to call alpha left, and z for 3, I'm going to call alpha right. So physically, they just measure the differences between positions of the two vertex operators on this side and this side. And then t left turns out to be the same one that we've seen on the previous slide, is this combination of the variables. It turns out we're actually missing one of the variables, the t right, and this is something that we can just integrate in. So this is somewhat of an arbitrary step in which we're just integrating in some variable that gives me 1. And the reason for doing that is that we can actually recognize the final answer would be of the same form as the one given by the unitarity cuts. Okay, so here's the summary. What we have at this stage is that we have this integral involving the variables alpha left, alpha right, t left, t right and the modular parameter. Okay, so first of all, we can integrate out this dependence on alpha left, which only enters through here and here. And that gives you directly the Veneziano amplitude on the left. Similarly, on the right, you get Veneziano amplitude with this combination. Then you can also integrate out the modular parameter, for which now that integral is very easy to do. It maps to some Henkel contour that you can do, and it gives you precisely this kernel that convolves T left, T right, and the external kinematics. And then we're of course left with T left and T right, and that resulting formula is exactly of the same type that we encountered previously using unitarity cuts by hand. And this is how it emerges from the worksheet. Let me perhaps mention, mostly to the experts, that tropical analysis was previously featured in various aspects of the string computations, but mostly in the alpha prime goes to zero limit. Okay, this analysis also tells you you can identify where the new thresholds open up. So this is something in the scattering amplitudes literature called the Lado analysis, and basically here we can perform the same analysis but on the worldsheet. So as I mentioned before, a new contribution, this continuously opens up whenever new term can contribute to the function trop being negative. And using this analysis, you can determine where are the new thresholds for your string amplitudes. And quite miraculously, you recover that the new thresholds are supposed to open up precisely in the places that you expect from field theory. And you also find that you're supposed to have these so-called anomalous thresholds. It's also a prediction of field theory that these are the thresholds that open up, but for unphysical kinematics. In fact, the whole analytic structure in the physical region is quite complicated, but it's entirely consistent with the field theory expectation. So here's the plot of the real part of the S and real part of the T. Every line here is a branch cut. So the blue ones are the anomalous thresholds, and the orange and the green are the normal thresholds. All this happens in the unphysical kinematics when both S and T are positive. And as I said, it's quite complicated, but it's entirely expected as well. Okay, so let me perhaps summarize that this strategy, going higher and higher energies, allows you to basically recover the formula that we've seen before, the complicated formula from the unitarity cuts, where the worldsheet computation gives you directly these coefficients that we couldn't determine before. So the first one is 1, as we've seen before, and then the other ones turns out to be polynomials in the Mandelstam invariants. So these polynomials basically encode the matter content of the particles that you exchange, and normally there would be a result of summing over all of them, and here they're sort of gifted to us by the formalism. And let me also mention that similar analysis can be performed for other topologies in all possible kinematic channels. But I will not have time to explain that in this talk. Okay, so in the last 10 or so minutes, I think we have some time to now use these results and analyze some of the physical properties of the imaginary parts of the amplitudes. Okay, so as I mentioned, in here we'll only focus on the planar annulus contribution in the S channel. So as I mentioned before, there's this overall p-factor of the gamma function that gives you double poles on every massive exchange. So of course, if we started plotting that, the plots would be polluted with all these double poles. So what we do in practice is for the visualization purposes, we multiply by the sine function that inserts a double zero at the position of every double pole. And also, whenever I will show the plot, it does not include the polarization dependence. Okay, so this is the picture that we've seen before. As I mentioned, the formula for the imaginary part that we recovered on the previous slides is entirely very fast convergent. You can evaluate it wherever you want, and you can densely cover this plot and beat off some interesting some interesting physics, and then we'll do some checks on this formula in the alpha prime goes to 0 limit and in various limits of in various directions. Okay, so this plot is of course quite showy, but it's very difficult to read off some physics from it. So let me just show you some slices for this plot. Okay, so here's plotting the major parts of the planar annulus contribution modulated with the sine function for various fixed momentum transfers. So for example, the blue curve is the forward limit as t goes to 0. And as you can tell, all of them kind of flatten out. And in particular, in the forward limit, the amplitude kind of really goes to a constant, or something that might look like a constant. But however, we have good evidence that the asymptotic behavior has not been reached. So everything here is plotted up to some energy, say in this case, s equals 7. And we believe that once you go to higher and higher energies, there will be some new features that cannot be seen in this plot. And let me also mention that every dashed line here represents a new threshold contribution that opens up. Okay, here's another plot. Instead of fixed momentum transfer, we're plotting things at the fixed angle. Okay, so for various angles. And this is where you expect the exponential suppression to kick in. Known from the work of Gross and Manes. And indeed, you can probably read off some exponential suppression from those plots, but we'll make it much more qualitative in the future slides. Okay, here's another interesting quantity. The string cross-section, or more specifically, is the planar annulus contribution to the string cross-section. So recall that the cross-section is related to the imaginary part by taking t goes to 0 and multiplying by 1 over s in any dimension. Okay, so what we can see from this plot here, the black curve is the cross-section that we're plotting, and as you can tell, it grows more or less linearly, at least at low energies. And moreover, what I've done in this plot is also split it up in different contributions. So there will be contributions from the mass threshold, first level and 0 level. These are the levels that are being exchanged in the intermediate channels. So one of the features that was a bit surprising is that these thresholds open up very, very slowly. So for example, if we look at this contribution here, which is the level 1 particle and massless particle, it's supposed to, the corresponding threshold is supposed to open up at s equals 1. But actually, its effects are opened up very, very slowly, and its effects are not visible only up to maybe 2 or so, and then it become more and more pronounced. Okay. Here's the plot of the so-called low spin dominance, which is something that we observed here at genus-one, and it's related to some previous work at tree level. So what we compute here are the partial wave coefficients, Fj, which are extracted from the amplitude by convolving it with the Gegenbauer polynomials. Okay. So J here is not the spin of the individual particles; is like the spin of the composite system of the two particle state that we exchange. Okay, so here we're plotting the imaginary part of this partial wave coefficient for various spins, J, as a function of energy. Okay, so let's focus, for example, at the scalar exchange, scalar coefficient. It is this blue curve here. And notice that this axis here is logarithmic. And what you can read off from this plot is that if you're in the region somewhere between 0 and 1, basically the scalar part dominates by a few orders of magnitude over spin 1, spin 2, and so on and so on. So that means if you only knew about the partial coefficients and for the scalars, you would not be making a large mistake if you just approximated your amplitude as just the scalar exchanges. And similar thing starts happening as you increase the energy. So for example, this is the spin 1. And we see that as you increase the energy, for example, to s equals 2, anywhere between s1 and s equals to 2, you only have to take into account the scalar and spin one exchange, and you would not be making a substantial mistake. And in general, what we observe numerically here is that almost all of the contributions come from partial wave spins j+1, which are of more or less smaller than a given energy that you consider. And this is the...
Is there any parametric or more precise statement here? It looks like just sort of numerical accidents. Is there some limit you can take to make this sharper?
Right, so we can fully analytically understand the positions of which spin diverges at which energy. So that we have classified. In fact, you can partially read it off from this diagram. But most of the sort of details of these curves are very difficult to understand, or at least we didn't attempt to understand analytically, so most of this is numeric.
Well, what I meant is, for instance, you said that for S between 0 and 1, you just need to know the scalar and the rest looks like small corrections. But small in what? Is there some parameter that could make those corrections arbitrarily small?
Good question. The only parameter that we have here is the alpha prime, because we're already fixing the kinematics. So I believe that once if you look at the specific point, there's no wiggle room. You can of course consider different string theories and see how, depending on if it's type 1 or type 2, how this changes. But I think there's no other wiggle room. That's a good question. Okay. Let me perhaps, since I'm supposed to close up soon, let me perhaps also mention the decay widths. So that's another thing that you can read off from those computations. In this case, the decay widths are computed by the coefficient of the double residue of this degeneration that we were computing before, essentially because it's the leading correction in the 1pi expansion of the Dyson summation, the same as in field theory, and then we can compute these decay widths as the decay widths are computed for a given level, so level 1, level 2, level 3, and so on. And then they're a function of t, which tells you about some kind of spin dependence of these widths. And we observed, so of course we recovered our agreement with previous analytic computations by these authors, and we also observed a curious feature that seems to appear that at the given mass level, the polynomials that we get seem to be almost exactly, but not quite t+1, t+2, t+3, and so on. Okay, so they look like the Pochhammer symbol, roughly. And in fact, we can use this intuition to approximate the amplitude, or use this observation rather. So using this, you would pattern match to the fact that the imaginary part of the double residue goes like this combination of the gamma functions. In fact, since the prediction for the exponential softness is supposed to be quite robust, we can use this to approximate the high energy fixed angle scattering. So if we just take this result and then reconstruct what the amplitude should be, so essentially what we've done is reconstructed the amplitude at integer points, and now we can extrapolate these integer points to high energy. If you just do it naively, you would find that the result is this, which matches with the exponential decay predicted by Gross and Manes in the late 80s. So here the exponential softness is modulated with the tree-level action, which is equal to this combination. Okay, so this is just an approximation. What you can do now is you can compare it with numerics. So you can take the approximation from the previous slide, and you can actually match it with the numerics, because it's much easier to compute the decay widths than the full amplitude. We can actually go to higher and higher energies. And for example, going all the way up to 14, you compute the ratio between the numerical computation and the previous slide, and then you find that they approach 1, meaning that the prediction of the exponential softness seems to be extremely robust in this limit.
Is there a question in Zoom?
There's a question in Zoom. So Emil is pointing out that there was a similar computation by Gross and Mende, which was done in the case of the closed strings. There was another prediction done by Gross and Manes, which is performed for the open strings. So here we're matching the open string contribution.
Okay.
It's actually interesting because in the closed string, at genus G, the prediction was that you're supposed to recover the tree-level action divided by G plus 1. But in the open string, there's the answer is not supposed to be divided by G plus 1. So we matched that here. That was one of the checks that we wanted to do. Okay, so I think this might be the last slide, in which we also flash that you can, of course, do with this computations, you can also match with the traditional alpha prime expansions. So this is the expanding in the low energy limit as opposed to high energy limit, and recover the full dependence on the amplitude, and then we match that with the known computations all the way up to alpha prime in the 8th order. With that, what we've done in this talk.
Can I ask a question? So you say that this high energy scattering result is not suppressed by genus?
That's correct.
How do I understand that? Because if for closed strings, it says that that's basically the softness of the momentum transfer. So the fact that it's not suppressed at higher genus is because you're basically splitting the momentum transfer among n intermediate strings.
That was the intuition, yes.
Yeah. So I guess it's a little surprising that there isn't a corresponding suppression of open string scattering. Is there some intuition for that?
I'm not sure if there's an intuition. In fact, I'm not sure if the intuition in the Gross-Mendel case is, I mean, it's a good intuition, but there have not been many explicit computations done, and in fact, not many done after the 80s. So one of the things that we wanted to do is put these predictions on a more quantitative grounds and actually compute the amplitudes and check.
Okay.
Yeah, perhaps we can discuss it later. Okay, so let me just summarize the talk. In this talk, we set out the goal of numerically computing the scattering amplitude at genus-one in string theory at finite values of alpha prime. And to this end, we discussed the analytic continuation of the worldsheets to the Lorentzian worldsheets, and then we proposed the specific integration contour. We've used the imaginary part of this integration contour to derive this procedure of computing the unitarity cuts of the worldsheet. And then we talked about the physical properties of the imaginary part, and we found some interesting stuff there. So with that, let me thank you for your attention.
Questions? We already had a few during the seminar, so if anyone wants to hang around, they can ask Sebastian more afterwards, but maybe we can just thank him again.
Sebastian, can you show us this most complicated contour that you mentioned?
Yeah, absolutely. I have a few slides. So the idea here is to recycle the computation of the single circle many times, infinitely many times. So let me assume that using the sort of technology that I was talking about in the main part of the talk, we knew everything, how to compute the integrals of these contours. And before explaining how to do the full contour for the real and imaginary part, I will have to go through some topics in number theory. Okay, so let me introduce this Fourier sequence. The Fourier sequence f sub q is going to consist of all irreducible fractions between 0 and 1, where the denominator is at most q. So for example, f1 is these two fractions, then f2 include 1/2, f3 include the 1/3 and 2/3, and so on and so on. So this way you can build up all the rational numbers. Okay. So knowing that, let me now introduce another notion called the fourth circles. And fourth circle C is going to be labeled by a fraction P over Q, and it's going to be a circle in the tau plane that is touching the real axis, this specific rational P over Q, with a specific radius. Okay, so radius is going to be 1/2 of 1 over Q squared. Okay, so it turns out that if you use the specific radii, that all of the circles sort of snugly touch each other in this nice fractal pattern. So for example, the circle if I choose P over Q to be 0 over 1, then I have this big circle in here that touches the axis at 0, and it has the radius of, 1/2. So this is this circle. And another example is this circle here, C of 1 over 2, which of course touches the real axis at 1/2, and it has a radius of 1/8. Okay, and then you can keep going. Okay, and then the reason why we care about this is that we know that each of those is in fact a modular transformation of the original circle. So C of 0 over 1 is the one that we know how to compute already. And then we will be interested in the next slides with these other circles. Okay, so this knowing these two ingredients, we can now define the sequence of contours. And these are called Rademacher contours. And this is something that has been encountered by mathematicians in the context of analytic number theory. So let me call the gamma sub q the following prescription for the integration contour. So we're going to follow all the fourth circles in the Fourier sequence f sub q from 0 to 1/2. Okay, so the simplest example is when we take q to be 2. This means we list all the fractions, as we've seen on the previous slides, between where the denominator is at most 2. So that is going to be 0 over 1 and 1/2. And then the prescription is we select these two circles, this one and this one, then we follow the first one until we encounter the next one in the sequence, like so, and then we turn around, and then we go back to 1/2. Okay, so this is of course the original contour that we've seen on the previous slides that we claimed is computing the correct the scattering amplitudes with the correct I epsilon. Okay, and now what we do is we keep deforming this contour to a more and more complicated sequence. So this is the contour gamma 5, in which to obtain it, what we have to do is we have to list all the fourth circles with the denominators at most 5. Okay, so we have 1/5, 1/4, 1/3, but also 2/5 and the 1/2. And the prescription is we follow the first one until we encounter the second one, then we turn, then we encounter 1/4, we turn, encounter 1/3, and then we keep going because the next number in the sequence is 2/5. And then from here we turn, and then we go to 1/2, and then we turn around. Okay, so at this stage you might think about stopping, but in fact, why not keep going? The reason why you want to keep going is that you wanted to be able to claim that you've encircled the whole circle. This is the only thing that we know how to compute. Say.
Why don't you throw away that little triangular piece between 1/3 and 1/2?
Yeah, that's a great question. So you might think that computing this piece here is wasteful because it computes 0, but we wanted to include it anyway in order to compute the whole sequence. So let me maybe tell you what the full sequence is. Of course, what we do here is we go to the limit as this q goes to infinity. In this limit, we now flow the whole integration contour in this fractal pattern. And now the statement is that we enclose every circle at every rational point exactly once. And then we also know that each of those circles can be mapped by a modular transformation to the one that we used in the computation of the imagined part. So now basically we can put all of those ingredients together, and as long as this procedure converges, which is far from obvious, this would give us some algorithm for computing the full string amplitude. In fact, we've implemented this in certain cases, and we've observed that the sequence indeed does converge, and it gives you some numerical results for the amplitudes and related functions like mass shifts. But the results are still preliminary, so I will probably ask you to stay tuned and maybe look out on the archive for these results. And I think this is all I wanted to say here. And I can thank you once again for this.
Yeah, thank you. Very clever.